Welcome to the class. Till time we have seen that there are different types of arrangements for a gas turbine based power plant, and then we have seen that there are different attachments also for a gas turbine based power plant. Now we are going to see in the today's class what are the different ways by which aircraft's performance can be measured and what are the different types of aircraft engines. So let us start with the today's class. So engine performance parameters. First is thrust. So let us consider that we are having an aircraft. Let us draw a schematic of an aircraft engine, and this is an aircraft engine where we are considering it as a control volume or practically a black box where there is some air which is coming with velocity Ca, and then there is jet which is going out with velocity Cj, and the area of the jet is Aj. Further, the atmospheric pressure which is acted upon the aircraft or which is present in the ambience of the aircraft from which it is breathing the air is Pa, and the jet pressure at the exit is Pj. So having said this as the operating condition of an aircraft engine, we can write thrust of the engine is equal to change in momentum. So thrust of the engine is equal to m dot A, which is mass flow rate of the air, into Cj minus m dot A into Ca. So this is the thrust. So m dot A into Cj minus Ca is the thrust produced by the engine. Further, we are assuming here that the pressure acting on the exit of the jet is almost equal to atmospheric pressure, or this is almost a static thrust. However, if we consider the pressure component of the thrust, then we get the formula for thrust also having pressure which is Pj, which is Aj into Pj minus Pa. So this is the thrust which accounts the pressure. Pressure is also accounted. Thus this is the formula for thrust. Now let us find out what is the thrust power. So thrust power is thrust into velocity, and we know that aircraft is moving with velocity Ca. So thrust power is equal to m dot A into Cj minus Ca into Ca. This is the formula for thrust power. Now let us move on and find out what is the propulsive efficiency of an aircraft. So here we have to first define what do we mean by propulsive efficiency. So eta P, let us say that it is propulsive efficiency of the aircraft, and then that is defined as thrust power which is generated by the engine divided by change in kinetic energy between inlet and outlet of the engine. So thrust power divided by change in kinetic energy is propulsive efficiency. Looking at the figure, we can say that m dot A into Cj minus Ca into Ca was the thrust, and then the change in kinetic energy was m dot A into Cj square into m dot A Ca square divided by 2, was the change in kinetic energy between outlet and inlet. So we have m dot A into Cj minus Ca into Ca. So these two will go to the numerator and m dot can be taken as a common. So we have Cj square minus Ca square. Further, m dot A can be cancelled and then we have Ca into Cj minus Ca divided by Cj square minus Ca square. This term we can write as Cj minus Ca into Cj plus Ca. So propulsive efficiency can be written as 2Ca divided by Cj plus Ca, since Cj minus Ca term gets cancelled. Further, simplified formula for propulsive efficiency is 2 upon 1 plus Cj by Ca. So this is the formula for propulsive efficiency of an aircraft. As per this formula, it is evident that if Ca is equal to 0, then propulsive efficiency is equal to 0. Further, Cj is equal to Ca would lead to propulsive efficiency equal to 1. So this is the definition of propulsive efficiency of an aircraft. Propulsive efficiency is one of the performance parameters of the aircraft engine. Next performance parameter of the aircraft engine is energy conversion efficiency. Let us define energy conversion efficiency as eta E, and that eta E is change in kinetic energy which is taking place between outlet and inlet of the engine divided by input fuel energy. And input fuel energy is known to us from the calorific value of the fuel. So change in kinetic energy is already known to us, which is m dot A into Cj square minus m dot A into Ca square divided by 2, and input fuel energy is mass flow rate of fuel into calorific value of the fuel, which is amount of energy liberated when unit kg of fuel is burnt. So having known this, we can write this formula as m dot A into Cj square minus Ca square divided by m dot F into Q. Further, this can be written based upon air fuel ratio of an engine as A by F into Cj square minus Ca square divided by Q. So this is the formula for energy conversion efficiency of an engine. So this is second performance parameter, rather in terms of efficiency of an engine. Now we will define a new parameter as overall efficiency of the engine, and overall efficiency is final output divided by initial input, and we will rewrite the formula for energy efficiency as 1 by 2 into A by F into Cj square minus Ca square divided by Q, and we will write overall efficiency as the ratio of thrust power of the engine, which is final output, thrust power which is final output, and basic input is input fuel energy, and so this becomes equal to propulsive efficiency into energy conversion efficiency. So in all, we are feeling that there is fuel which has chemical energy in it, and this fuel's chemical energy is used to convert the kinetic energy of the air, and this kinetic energy gives thrust power. So there is an efficiency which is between thrust power and kinetic energy, and that we are calling it as propulsive efficiency. There is an efficiency between fuel energy and kinetic energy, that we are calling it as energy conversion efficiency. And then there is overall efficiency which is between thrust power and fuel energy. So these are the three efficiencies which are related with the performance of the engine. However, we should note here that the only thermal efficiency of the gas turbine power plant should not be thought for the best performance parameter. We have seen that there is thermal efficiency of the engine, and which was W net upon Q in, and this should not be thought as the best performance parameter for the engine, since there are various requirements for designing a given aircraft engine. So there is a requirement something like static thrust or thrust at the sea level, where we encounter maximum temperature in the engine. Further, there is requirement for the takeoff kind situations. So in such cases we get different performance parameters, and those performance parameters should also be having equal weightage while designing the aircraft engine. From the thrust equation we can see one more thing, that we said that thrust is equal to m dot a into Cj minus Ca. Here we can see that thrust of an engine can be increased by changing the velocity more. This is one way to increase the thrust if Cj minus Ca is high for given m dot a. This is one way where we are handling small amount of mass and increasing large velocity change and bringing in large velocity change. This is one way to increase the thrust, and other way to increase the thrust is to increase the mass flow rate for a small or given velocity change. So here we are handling more amount of mass but having small change in velocity change, small change in velocity. So these two are the basic ways by which we can get different thrusts, or we can increase the thrust, and based upon this concept we have different types of aircrafts. So as what we have seen, this also becomes one of the parameters for designing an aircraft. Basically we might need to handle more amount of mass of air, something like if we are traveling at lower altitudes we will handle more amount of mass of air as it is handled by the turboprop engines or the piston prop engines. They handle more amount of mass but they do not bring in more amount of change in velocity. So but if we consider turbojet like engines, they handle less amount of mass comparatively but they bring in large change in velocity. So only thermal efficiency should not be thought as a basic parameter. Further, at cruise speed or at level flight, then at that time economy becomes more important and all such parameters should be considered. Then in one such parameter is thrust specific fuel consumption. So SFC is defined as mass flow rate of the fuel, which is fuel mass flow rate, divided by thrust power, divided by thrust, divided by thrust. So this is m dot f in divided by T. Further, we can write down it as m dot f divided by m dot a into m dot a divided by thrust. We are multiplying and dividing by m dot a, and this becomes fuel air ratio of an engine into m dot a divided by T. So, SFC equal to fuel air ratio into 1 upon small t, or we will say it as tau, and this tau is specific thrust. Tau is specific thrust, and then that is T upon m dot a. This is also termed as thrust specific fuel consumption, TSFC. So, here we can use this thrust specific fuel consumption to compare between two engines which are operating at two different conditions. Then let us consider our aircraft engine where we are redefining thrust. We neglected few terms and we will redefine the thrust by considering the terms which we did not account. So, this is an aircraft engine. We are seeing that air is coming with CA velocity, going with CJ velocity, and then jet area is AJ, and then we have m dot A as mass of air, but while leaving we have added m dot F amount of fuel. So, m dot E is exit mass flow rate. Having said this, we can redefine the thrust as change in momentum or between inlet and outlet. So, we have outlet momentum as m dot E into Cj minus m dot A into Ca. Further, the component of the pressure remains same. So, thrust becomes m dot A plus m dot F into Cj minus m dot A into Ca plus Aj into Pj minus Pa. So, let us take m dot A common, and then we get 1 plus fuel air ratio into Cj minus Ca plus Aj into Pj minus Pa. So, what did we derive in earlier case, or we said in earlier case, was only Cj minus Ca. We had not accounted this term which basically accounts air fuel ratio. Here our assumption was that air fuel ratio is negligible. So, when we accounted air fuel ratio, the formula got changed to T is equal to m dot A into 1 plus F by A, which is fuel air ratio, into Cj minus Ca plus pressure component of the thrust. Now, let us use this formula for finding out takeoff thrust, where we are again going to discard some more terms. So, takeoff thrust is also called as static thrust, and then that thrust is actually obtained at very low speeds or at the static condition of the engine, and then that thrust is basically thrust upon m dot A. So, if we neglect fuel air ratio to be 0, if we assume Pj minus Pj is equal to Pa, then we get formula. Further, we will assume, since we are considering that aircraft is at static condition, so Ca is equal to 0, considering these three. So, this term will go, then this term will go, and this term will go. Further, this will get divided by m dot A, and this leads to the formula as Cj. So Cj is the jet velocity which is giving us the thrust. Cj is the jet velocity which is giving us the thrust per unit mass flow rate in the static condition of the aircraft. So let us use the energy conversion efficiency and understand this further. So energy conversion efficiency is equal to half m dot a Cj square divided by m dot f into q. We know that the formula for energy conversion efficiency was change in kinetic energy divided by fuel energy, but in the change in kinetic energy we are neglecting Ca. So this formula is basically for static case. For the static case we have only 1/2 m dot a Cj square divided by q. So here this formula leads to Cj square equal to 2 into energy conversion efficiency into q into m dot f divided by m dot a. So we get m dot a into Cj is equal to 2 into energy conversion efficiency into q into m dot f divided by Cj. So m dot a into Cj is basically thrust. So this is thrust, this is equal to T. So we know now T is equal to 2 into energy conversion efficiency into calorific value of fuel into mass flow rate of fuel divided by Cj. So from this formula it is evident that for given energy conversion efficiency and fuel used and further mass flow rate of fuel, thrust is inversely proportional to the jet velocity. Thus it means that if we handle more amount of mass and have a smaller velocity jet, then we can have more amount of static thrust. So this is one of the performance parameters of the aircraft. So next parameter what we can see is called as aircraft range. So when we are considering range, we are meaning that there is certain amount of fuel in the aircraft and that aircraft is traveling from a place to the other, and for a given amount of fuel the distance travelled by the aircraft. This is what we mean by saying a range of the aircraft. So for range of the aircraft we are targeting the cruise condition or level flight, and for the level flight there are two things. One is lift is equal to weight, and let L is equal to lift and weight is equal to mg, where m is mass of the aircraft, and further there is drag equal to thrust. So let d be the drag and thrust be T. So we can use this and find out the derivation for aircraft range. So T is equal to D, so D by L into L, we are multiplying and dividing by L. So this gives us this D by L is drag to lift ratio and L is equal to mg. Further thrust becomes mg, which is weight divided by lift to drag ratio. Let us multiply both sides by the aircraft velocity. So T into Ca is equal to mg into Ca divided by L by D, and we have seen that this we will number it as 1, and then let us bring the formula for overall efficiency again, and then we know overall efficiency was for static condition there was one formula. However, in general we know it as m dot a Cj minus Ca into Ca, which is thrust power divided by m dot f into q, which was fuel input energy. So here this part is thrust and this is aircraft velocity. So this is T into Ca divided by m dot f into q, and this leads to T into Ca is equal to overall efficiency into m dot f into q. So considering this as formula 2, so considering formula number 1 and 2, we get overall efficiency into m dot f into q is equal to mgCa divided by L by D. So using this we can write down mass flow rate of fuel is equal to mgCa divided by L by D into overall efficiency into Q. So this is the formula for mass flow rate of the fuel. But what do we mean by mass flow rate of a fuel? So that is what it is getting consumed, and so m dot f we can write it as negative of dm by dt, where m is the total mass of the aircraft as we have used it for the formula for lift. So total mass of the aircraft is changing with respect to time, and that is due to the consumption of fuel. Further, we are interested in finding out range. Let S be the distance travelled in the direction of velocity, and then the velocity Ca is equal to ds by dt. So using these two things we can write down m dot f is equal to minus Ca m dot f into dm by ds. So these two things, this is formula number 3, equation number 4. So equation 3 and 4 would lead us to this, where we will have minus Ca into dm by ds, and then that is equal to mgCa, that is equal to mgCa divided by L by D into overall efficiency into Q. So we can use further and say that dm by m is equal to ds divided by L by D into overall efficiency into Q into G. This will have minus sign. Here Ca is getting cancelled. So now let us assume that, or let us take it for granted that L by D, overall efficiency and calorific value of fuel, and G are constants. So having said this, and further M1 and M2 are initial and final masses. Having said this, we can get it as ln of M1 divided by M2 is equal to Gs divided by L by D into overall efficiency into Q, where S is the distance travelled by the aircraft. So S becomes overall efficiency into L by D into ln of M1 divided by M2 into Q divided by G. We again will use the formula for overall efficiency, which was Tca divided by m dot f into Q, where we will say it as equation number 5. We will say that overall efficiency into Q was Tca divided by m dot f. So keeping this equation number 6. In equation number 5 we will get L by D into ln of m1 divided by m2 into T by m dot f into Ca by G. So this formula is for range of the aircraft, where we can see there is a term which is T upon mf, m dot f. So that is basically related with specific fuel consumption, and so this is m dot m1 L by D into ln of m1 minus m2. So this is thrust specific fuel consumption raised to minus 1 Ca by G, where thrust specific fuel consumption or specific fuel consumption was m dot f upon thrust. So it is evident from this formula that for a given speed of the aircraft, range decreases if thrust specific fuel consumption increases. So range of the aircraft is inversely proportional to the thrust specific fuel consumption. So we have seen that there are different parameters like overall efficiency, energy conversion efficiency, thrust power, then we have overall efficiency, we have specific fuel consumption, we have range of the aircraft as different parameters which are deciding the performance of an engine. Based upon that, there are different engines which we are going to see. The aircraft engines, first is the turboprop engine, where we have first is piston prop engine, where this engine has the piston engine, which is our automobile engine, and this automobile engine is connected with a propeller, and the motion of the propeller would be governed by the engine, and then we have basically thrust generated due to the motion of the propeller. So this engine is piston prop engine. Basically here we are not having any jet to produce the thrust. Here thrust is produced from the propeller. This engine is more suitable for lower altitudes and at lower speeds. Further, this engine also cannot be used for high thrust applications, since at those thrust conditions the weight of the piston increases, and this engine also cannot handle large amount of mass flow rate, as what we had seen while differentiating between the reciprocating engines and the aircraft engines based upon the turbo applications. So second is turboprop engines. So in the turboprop engine we have major thrust coming from the propeller, and this propeller is rotated by the turbine. We can see here a typical arrangement as what we had seen earlier, and then that arrangement was triple spool arrangement, and in the triple spool arrangement we had seen that propeller will be connected by lowest speed turbine, compressor, low pressure compressor will be connected by intermediate turbine, and high pressure compressor will be connected by high pressure turbine. So here we are having propeller, and then this unit is the compressor, and then this is combustor, and then this is turbine. So most of the energy extracted from the fuel and the flow is used to rotate the propeller, and rest is passed through the nozzle. So there is partially small amount of thrust generated from the nozzle as well. So turboprop engine gets major thrust from the propeller, and this engine also gets used at the low speed applications and lower altitudes. The problem at high speed applications is for the propulsive efficiency of the aircraft, further the noise of the propeller becomes an issue and it needs to have a special design of the propeller. So turboprop engines are not generally used for high speed applications. Basically, if we see the schematic of this aircraft is as what we could draw. This is the propeller, and this propeller is connected with a gearbox to a compressor and then air goes parallelly into the compressor. Then there will be combustion chamber, and then after the combustion chamber then there will be turbine, and then air would be passed from the turbine to the nozzle, and then this nozzle is low speed exhaust nozzle. So this is typical schematic of a turboprop engine. So next is turbofan engine, and in the turbofan engine we have fan which is connected with the low speed turbine. This is fan, and then there will be some air which is going from the fan and getting compressed further, and then it is following a route which is called as cold path, and then that is generating a thrust which is called as cold thrust, but some air will go from the fan into the compressor. So this is compressor. After the compressor it will go into the combustor, and then it will go over the turbine. So this being a turbofan, so some part of the thrust will be from the fan and rest of the thrust will be from the jet, so that is from the nozzle. So this aircraft is basically having advantage of having lower noise due to presence of fan. So here we can draw schematic of the aircraft like this. So this is fan, and this fan is practically connected with a compressor, and then this compressor is passing the air to the combustion chamber, and from the combustion chamber air will go to the turbine, and after the turbine it will go to the nozzle, and this is moderate speed nozzle. This engine is generally used at moderate altitudes and moderately high speeds. Then we have turbojet engine. Turbojet engine has complete thrust based upon the jet, and this has components like compressor, and then it has combustor, and it has turbine and nozzle. So there is no propeller, there is no fan, so complete thrust is generated using the jet, and so this is a turbojet engine, and here this engine is generally used for high altitude and also at very large speed applications. And then we can draw simplest schematic of this engine, where we have compressor which will take air and it will pass to the combustion chamber, and then it will pass to the turbine. After the turbine it will go into the nozzle, where we have this as high speed nozzle. Practically turbojet engines can operate at supersonic speeds, so this engine would have a nozzle which would lead to have a jet which is a supersonic jet. Then last engine what we would be seeing here is a ramjet engine. Basically ram effect is the effect where the inlet momentum of the air is used to compress it to avoid the rotating compressor which is present at the intake of the engine or at the entry of the engine. So this ramjet engine doesn't have any moving part, so it compresses the air with its momentum. So at the inlet there will be a duct which will compress the air to the desired pressure and desired temperature, and then fuel will be injected as what we can see here. This is fuel, and then this would lead to combustion, and then this engine would generate a jet through the nozzle. Practically, ramjet engines are parasite engines which would operate at supersonic speeds, since we will have supersonic entry of the air and then the jet will be obtained after combustion of the fuel into the engine. Having said this, there is one more type of an engine which is called as prop fan or unducted fan. Prop fan or unducted fan. So this engine is basically having a compressor which will take the air and then it will go to the combustion chamber, and after the combustion chamber there is a turbine, and then there is one more turbine, and then there will be one propeller which will be fitted and connected to the low speed turbine, and one propeller is connected to the high speed turbine like this. So this engine has propellers which are connected, counter rotating two propellers which are multi-blade propellers which are connected to the turbines, and they generate the thrust. So this is also called as prop fan or unducted fan kind of propeller. However, this kind of engines need special attention for design of the aerofoils or section of the propellers. So having said this, we can note down the engines and then their corresponding limitations. So piston prop, and then we have turboprop, then we have turbofan, then we have turbojet, and then we have ramjet. So these engines, and in this direction we are having increase in speed of aircraft and jet, and in the same direction, however, we have decrease in mass of the air handled. So piston prop handles large amount of mass as equally by the turboprop. However, ramjet and turbojet would handle lower amount of mass than the piston prop engine. So if we plot a graph of altitude versus Mach number, where Mach number is defined as speed of the aircraft divided by local speed of sound. So this is turboprop, this is turbofan, and here we will get turbojet, where this range we will have around 0.5 Mach number, and we can go around 6,000 meter of altitude, and then it is 10,000 meter of altitude, and here we will have Mach number lower than 1 or around 1, and then turbojet engines would go around 20,000 altitude, and then they can also go for the Mach number of 2.5 2 or in that range. So this is where we can see that turboprop engines are operating at lower altitudes since they handle more mass flow rate and their thrust is based upon the amount of mass handled. Further, if we plot propulsive efficiency versus flight speed in meter per hour, flight speed, then we can see that propulsive efficiency is like this for turboprop engines, but turbojet engines would have this kind of propulsive efficiency trend, and then we have two trends for the turbofan engines. So this turbofan engine is low bypass and this turbofan engine is high bypass. Basically here we mean by bypass that the large amount of air, the amount of air which would pass through the cold circuit and generate the cold thrust. So lower amount of air would pass through the cold circuit and more amount of air would pass through the turbo part and generate more thrust. So this is the trend of propulsive efficiency and speed of the aircraft. So this is how we have seen that there are different kinds of aircrafts and then there are different performance parameters which are needed to evaluate performance of an aircraft. So next we will see in the next class. Thank you.